Good day, folks. Here's another Newton's second law question. It's a system. It says a sketch below shows an apparatus which can be used to determine the gravitational acceleration. So the investigation was the gravitational acceleration here. Two different masses M1 and M2 are attached by light massless intensible cord which hangs over a frictionless pulley shown in the illustration below. The masses are initially at rest. So guys, when the masses are initially at rest, that means that their initial velocity is zero. Guys, the system here guys, it's moving this direction, right? So we choose this direction as what? As positive. We choose this direction as positive. So in this side, down is negative, and this side up is negative, right? It's very important that now the system, guys, as I've mentioned in the previous video, that they accelerate in the acceleration is the same. Now it says ignore the effect of a friction and masses of the cord and pulley. State Newton's second law in terms of acceleration. Guys, check the exam guideline. I'm not going to waste time on that. Now it says when the masses are released from rest, the system moves through 0.245 meters in 1 second. So this M2, it moves downwards to the ground, this displacement, and it was initially at rest. Initial velocity is 0 and the final velocity we do not know. And how long it took that? It's 1 second. It's mentioned there. Now 2.1.2, it says draw a label free body diagram. It's very important that for M1, so M1 is going down, and we represented that object by a dot. It's going down. It's pulled by the gravitational force, so the magnitude of the gravitational force will be bigger, and then there's a tension force that is up. It's going to be smaller, and this is M1. And then I would like to do for M2 as well, even though it's not asked. So for M2, it's going upwards. It's going upwards by the tension force. It's going to be bigger, and the gravitational force will be down, and it's negative, right, according to the choice of our direction. Now in 2.1.3, it says calculate the value of gravitational force. Guys, in order to calculate the value of the gravitational force here, we need to know what is an acceleration of the system before we get the gravitational acceleration. In other words, here we are proving the gravitational acceleration is 9.8, so we should get the answer that is 9.8. But the acceleration of the system, we have to get it first. So how are we going to get the acceleration first of the system here? We have time here, and it's 1 second, and we have the displacement that is 0.245 meters of mass 2, no? For mass 2. And so which equation are we going to use in order to get that acceleration? And another thing that we know, its initial velocity, it was 0, and the final velocity we do not know and we do not have. So which formula are we going to use? We're going to use this formula that says change in y is equal to v initial change in t plus half a change in t squared. We wanted the acceleration here, not the gravitational acceleration. So our displacement is 0.245. Initial velocity is 0. That means all this time side will be 0. And then the acceleration here is the one that we're looking for, and the time is 1 square. So what are we going to have here? We're going to have 0.5 times 1 square is going to be 0.5a, 0.245, and then we divide by 0.5 both sides. So when you punch that in the calculator, it will be 0.245 divided by half. It will be acceleration of the system the acceleration of the system will be 0.49 meters per second square. So now that we have the acceleration of the system, now we can go and do the simultaneous equation to calculate the gravitational acceleration. So let's start with mass 1. We'll say F net is equal to ma. And then what are the forces that are acting on mass 1? It's these two. And you must remember on mass 1, there's a tension force that is going up, that is positive, and there's a gravitational force that is negative. So we'll have the tension force that is upwards and the gravitational force that is negative equal to ma, and then we substitute. T we do not know, and the mass of that side is 1.9 times 1.9 times g. It will be 1.9 times g because we're looking for g. And here in this side the mass it's 1.9 times the acceleration there, it's 0.49. So 0.49 times 1.9. So the answer in this side it's going to be 0.931, and in this side it will be T is equal to 1.9 G. So what are we going to do? We'll say here, we'll say tension is equal to 0.931 plus 1.9 G, right? And this will be equation 1. That will be equation 1. So doing the equation 2 for mass 2. So we'll say F net is equal to ma, and then the forces that are acting in mass 2, it's the tension force and the gravitational force. But now the gravitational force is positive and the tension force is negative. So the mass 2, it's 2.1, it's going to be 2.1 times g. We do not have the gravitational acceleration, minus the tension force, it's T, equal to the mass, it's 2.1 times 0.49, the acceleration that we calculated. So 0.49 times 2.1, it's 1,029, and then we'll have 2.1 G minus T. So we can leave that as equation 2. So now what are we going to do? We're going to sub equation 1 into equation 2. So we'll say 2.1 G minus, we insert that is going to be 0.931, we insert this, plus 1.9 G equal to 1,29. I hope you are following. So it will be 2.1 G minus 0.931 minus 1.9 G equal to 1.029. So these two when 2.1 minus 1.9, so the answer it will be 0.2 G equal to 1.029 plus 0.931, and the answer will be 1.96, 0.2 G, and if you divide by 2 both sides, so your G will be 9.8 meters per second square. Right, now let's go back to 2.2. 2.2, it says a spaceship M a spaceship of mass mkg leaves the planet A and set out into a space towards a newly discovered planet B, as shown in the diagram below. So here's planet A and there's planet B, the newly discovered one. The spaceship moves from planet A to planet B. So it shows there. So it says after traveling 60% of the way to planet B, it says it travels 60%. So it's not halfway, it's above halfway, it's 60%. The commander discovered that the net force of the two planets on spaceship is zero. So it means the force that is acting on this and the force that is acting on the spaceship is zero when it's 60%. It's 60% of the way of planet B. Now, the question, it says give reason why Newton's law of universal gravitational is referred as an inverse square law. So the reason for that, guys, the reason for that, um, the Newton's universal is referred as an inverse law, it's because the gravitational force is inversely proportional to the squared distance, right? That's the reason. It's inversely proportional to the squared distance between the masses. That's the reason for that. You can write that as an answer, or you can write the universal gravitational law. It says the gravitational force. If you can write the universal gravitational law there, you'll get the answer. Right? Now, in 2.2.2, it says show by means of an appropriate calculation that the ratio of masses of the two planets given, M1 and M2, it's 9 is to 4. The ratio is 9 is to 4. So what do you need to understand? You need to write the formula first for universal. You get the mark for that, for the formula. And then what you need to understand from this is that when the Fnet, says Fnet is the force of planet B on the spaceship, force of A on spaceship, which is S, it's negative because it's going in this direction, right? And then plus the force of planet A. No, there's a force of planet B on A. Okay, let me show you here. The force of planet B on A, of planet B on the spaceship, it's going in that direction, is negative, and the force of planet A on the spaceship is positive in that direction. So here, let me rewrite it again. The Fnet is the Fnet of planet B on the spaceship is positive. It's negative because it's going from right to left. Plus the force of planet A on the spaceship is positive. So we are told the Fnet is 0. So what is going to happen here? You are going to have the G mass B times the spaceship, the mass of the spaceship, divided by r squared, plus G mass of planet A multiplied by the planet of the spaceship divided by r squared, and then we take this to this side, so it will be G mass of B E multiplied by the mass of spaceship over r squared equal to G mass of planet A multiplied by the mass of the spaceship divided by r squared. So what's going to happen? There will be cancellation. The G and the G will cancel, and the mass of the spaceship and the mass of the spaceship will cancel. So we'll be left here with mb divided by r squared equal to ma divided by r squared. Now you need to be careful when it comes to this. Now, Now, we were told the mass of the spaceship, from A to B. The mass of the spaceship. Okay, let's look at here. From A, from where it is, from A, it's 60%. So if it's 60% here, that means here it's what? It's 40% to B. It's 40% to B. Let me rewrite that so that you can see. So the spaceship, let's say the spaceship, it's here. It's here now. If it's here, it's 60%. It traveled 60%. And then from here to B, the distance, it's going to be what? It's going to be 40%. So in terms of percentage, that will be, the distance will be 0.6. So for B, we'll have the mass. The masses we do not know. It's mass B. For mass B, the distance will be 0.4 r. 0.4 r squared, because it's 40%. The distance that it still needs to travel, or the distance between them. For mass A, the distance between them, it's 60. The 60 divided by 100 is going to be 0.6 r squared, right? So if you do the math there, so we are going to cross multiply. You are going to have mass. You are going to have when you cross multiply the mass A times 0.4 r square, that, and you have mass B multiplied by 0.6 r. Then you will have MA times by 0.16 r squared. Here in this side you have MB times by 0.36 r squared. So now remember, they said we should prove that mass of A is to mass B is equal to 9 is to 4, the ratio. So now this comes from, it has to be mass of A divided by mass B equal to 9 divided by 4. It has to be like that. This comes from that, so we have to do that. So now in this side, which is this side, I have to have the mass A divided by mass B. So this is what I'm going to do. I'm going to divide by, I'm going to divide by mass B in this side. I'm going to divide by mass B and also divide by r squared. This side I'll divide by, this side I'll divide by, let's do it like this. So let's divide by 0.16 r squared, 0.16 r squared, and since we want the mass A over mass B, we'll divide as well by mass B. We'll divide by mass B as well. So this and this cancel, and this and this cancel. So in this side you're left with 0.36 divided by 0.16. This side you have mass A over mass B. How? This and this cancel, this and this cancel. So that's what you're going to be left with. So now, in order to get this ratio, that is 9 is to 4, we'll find the factor, which is this factor. It's going to be 0.04. So I'll divide that by 0.04 and divide that by 0.04. So 0.36 divided by 0.04 is going to be 9, and 0.16 times by 0.04 is going to be 4. So the fraction, when you change it into a ratio, it will be mass A and is to mass B equal to 9 is to 4. We're proving that